Okay, welcome to Wednesday morning. One thing that I wanted to do today, before we get started on the efficient algorithms lecture, is I wanted to talk a little bit about the assignment, the midterm assignment thing, because I think there's some misunderstanding about what's expected. So let me go ahead and share a brief example of what I've kind of pulled up here. Okay, so those of you who were in CSE 102 last year, some of this will kind of look familiar, but it's just a very simplified version of the bank example. So again, this is a system that you're not allowed to do for the midterm assignment because it was last year's semester long project, semester long assignment, just like this year is the store example. So you're not allowed to do the bank, you're not allowed to do the store. Okay. Now, you are well within your rights if you want to create this, right? To create the bank class. Well, okay, you're not to do the bank. To create your classes, to create, your getters and setters and all of your methods and stuff. But that's not required. That's not what the midterm assignment is. It's not creating this code. Okay. What the midterm assignment is you describing the system that I should create if I was your student. You're the teacher. You're creating an assignment. You're going to give it to me as an example. Okay, as you're going to give it to me for me to create. You need to define what classes I should be creating if I were a student. You need to be telling me what attributes those classes should have. You need to be telling me what methods those classes should have. And then when I say show some examples, this is an example of how the bank would be used. So imagine that if the assignment required that we create a bank class, we have a customer class, and that banks can have customers. So let's say I said, okay, one of the requirements was the bank should have a method called add customer that takes an ID for the customer and takes a name for the customer. And what's going to happen is this method should create a customer object and then put it into an array list or a set or a map or whatever, right? Your choice. But it adds a customer to the bank list of customers. And then the bank should also have a method where I get a customer, all right? And I can return a customer object. And then notice here, just some examples. I'm going to say, okay, I'm going to compile it. And it works. And then when I run it, okay, when I say display the bank get name, oh, I get my bank. Great. That's what I expect, right? When I display the customer get name for the customer object, I get customer one. And so according to the examples here, it seems like the code works really well, right? It seems like it creates the bank object, it creates the customer object, and it adds it to the list. Okay. All right. Now, this is what I would like to see inside of your description is how could I use this? Is the code correct? I don't know. You're not required to submit this part. Okay. You're submitting a description of how I can create something. Okay. So another thing that you might notice is, though, if you look at the examples, and by the way, this is in this midterm example folder inside of the lecture examples folder that you all should have access to on the Google Classroom, right? Notice that the bank, that seems to work. That seems to work. But notice that the get name method, that's not right, is it? This should not return a string value. This should return the name, right? But does it work here? Yeah, it sure does. It runs exactly like I would expect it to run, right? It gives me the name, my bank, right? Okay. So when you go to make these examples, if there is some like calculated thing, like if I wanted to find out what the customer balance was, for example, you can just return a static value for showing the examples. You don't have to implement this bank class, right? You don't have to implement the classes yourself, except for showing the examples, okay? But again, one of the things that this hopefully will also show, the fact that I'm giving you access to all of this, will also show you that just because your code runs on your computer and runs according to the examples that I gave, doesn't mean that it's correct. In fact, if we look over here, all right, if I were to comment out this test, this is basically the test that you think we're running. Create a bank with a name, my bank, with the address, my bank's address. And you think that we're running this. Right? Yay, all my tests passed. Wonderful. But what happens if I try to create a bank with another different name? And it should be my new bank name. My new bank name. Notice that when I run this now, I get a failed test case. Why do I get a failed test case? Because this worked for the example, but it did not work for another possible input to the bank constructor. Okay. So for those of you who, whenever you ask these questions like, well, why did I get this many points? Well, it worked perfectly according to the example. This is why in the assignment instructions that I give, I always say, I write it every time, do not rely just on the examples given in the assignment description, because we're not going to just use those examples. We're going to use other examples and make sure that it runs properly, right? Okay, so I hope this is a little bit clearer now that what we're asking for is an assignment description. I don't have one easily available, but what we're asking you to do is to describe a system. Okay, the classes, the interfaces, the abstract classes, what attributes, what methods need to be inside of those classes, and then show an example. Again, this example code works, right? This example code, for the purposes of describing the example system, works fine, right? It displays what I want it to display. Doesn't mean the code's correct. It just means that it displays what I want it to display. Okay, so you would show me this as an example, and you would show me this as an example of expected output. It's my job to make sure, it's my job as the student to make sure that when I create that method, that I create it correctly instead of something like this. Okay. All right. If you have any more questions, let me know. I really hope this clears things up, because I think there was some confusion. A lot of you have been sending me like Java code and saying, is this correct? Is this correct? It's your system. I don't get to decide what I'm not doing this stuff down here. Okay. This is, you're not giving me this stuff down here. I don't give you access to my solutions for these classes, like for the store class and the customer and the product class. I don't give you my solutions to that. What I give you is I give you an example. So you're the teacher. You're giving me a description of the system with certain requirements, with certain, like it has to have the 6 classes, it has to have one of them abstract and so forth. Okay. So you're giving me a description of the system, and then you're giving me an example of how you would use your system. And make sure your example's thorough. Like if the bank needed to have customers and accounts and all kinds of other things, for those of you who were in this class last year, you know that the bank system was much more than just a bank and a customer, right? There was a lot more to it than that, right? Make sure that you make your example and make sure that you make your system more complex than just 2 classes, right? Okay. So even, well, I guess what I mean is your system has to be more complex. Make sure that your example shows enough of your system that I get an idea of what you expect from me as the student. Okay. All right. So that should be it. I'm hoping that that's clear to most of you. All right. Again, if you have any questions, please, please, please do not hesitate to let me know. And what we'll do now is we will move on to developing efficient algorithms. Now, this is not an algorithms course in and of itself. All right, we're not going to get into the like really deep topic of algorithms, but I do want to introduce this to you. I do want you to understand that just because 2 things do the same thing doesn't mean that they're equal. Okay, so if you want to look through this at some point, you're welcome to it. Okay, so the idea is that one thing I've often said is there's more than one way to complete a task. There's more than one way to successfully, correctly complete a task, right? So for example, what if I said, I want to go to Ankara. So before I moved to Antalya, my family and I lived in Ankara. And it's a wonderful place if you've lived there. If you've never lived there, you might not think so. But anyway, so if I wanted to go to Ankara, how many ways could I do that? Right? There's lots of different ways. If you were to say there's only one way to get to Ankara, then you guys would probably agree with me that that's not correct. That if I wanted to take an airplane, now, okay, obviously right now I can't go to Ankara. I get that, right? I have to wait until the lockdown is completed, right? But if I wanted to go to Ankara under normal conditions, I could take an airplane. I could take a bus. If I have a car, I can drive. I could walk, right? So if you know me, walking is not something I'd want to do to get to Ankara, but it is still an option, right? And so the question is, what is the best way to get to Ankara? Well, it depends, right? It depends on, is the most important thing that I get there quickly? Well, then maybe flying would be the best option. Is the most important thing that I get there inexpensively, right? Or cheaply, or using the least amount of money? Well, then maybe I guess walking might be the best, although it'd take a long time, and I might run out of energy on the way. But maybe driving or taking a bus would be cheaper than flying, right? All right. So just because there's the problem is get to Ankara, the solution, there's not one. There's lots of different ones. Okay. So one thing that we consider when creating a digital solution, a computer solution, right, is execution time. Okay, this is executing time. We might also refer to this as execution time. And it's the idea is, how much time will it take for something to complete? Okay, how many tasks, how much time in terms of, generally we think in terms of seconds or milliseconds, does it take for some solution to complete the answer to a problem? Okay. All right. Now, you might think, well, what I'll do is I'll take one solution, I'll just run it, and I'll see what happens. And if it takes 2 seconds, but then I run the other solution and it takes 4 seconds, then obviously the 2 seconds one is better, right? The problem with that, the problem with thinking of things that way is that, one, there could be a lot of different things going on a computer. Something that runs fast on your computer might not run as fast on mine, depending on if I have other things going on at the time, right? I'm sure some of you have figured out that while you're on this call, some other things on your computer might not run as fast, And a lot of it's because the call right now is using up lots of bandwidth and lots of internet, and there's lots of processing going on in getting this video to your screen, right? And so something else that normally might run very quickly, like your other things that you're doing right now, right, might not be going as quickly because you have this call up right now. And the other thing is that the execution time could be dependent on specific input. What that means is, right, is that if certain things are true, then if the data comes in a certain format to start with, then it might be then certain algorithms will be faster than others. And I guess what I mean is, so what the example that it gives is, if the element to be searched happens to be the first in the list, linear search will find the element quicker. So if it just happens to be somewhere early, then a linear search passing through from beginning to end would be quick. So for example, if you were to grab a dictionary, like a physical paper dictionary, right, and you were to try to look for the word aardvark, okay, aardvark starts with AA, it's AAR is how that word starts. Okay, would you want to start in the middle of the dictionary, like in a binary search fashion? Middle of the dictionary, then move to the first quarter, then move to the first eighth, and so forth, until you finally get down to the very first word in the dictionary? Probably not, right? That wouldn't be the fastest way to find that particular word. Okay? In the same way, you might say, if I were to ask you what's the fastest way to travel from one place to another, you might say, well, airplane. What's the fastest way for me to get to Ankara? It's the fastest way for me to get to Istanbul. It's the fastest way for me to get to London. It's the fastest way to get anywhere. Okay, well, should I go get on an airplane to get to Konyaaltı? Right? No, of course not. That wouldn't make any sense, because it would take more time to get to the airport than it would for me to drive over to Konyaaltı. But by the way, I'm in Murat Pasha right now, so not Konyaaltı, right? The specifics of what the data is. In my example right there, the data would be start location and end location. All right, so it could change based on what we're doing, or what the data is, what the example is. Okay, so we can't just run one solution and see how fast it is, run another solution and see how fast it is, because there could be some problems with that, right? So in the example of the linear search and binary search, if we happen to look very early in the linear list for a lot of data, right, then we may end up with this wrong conclusion that on average linear search is faster, when in actuality what we'll find is binary search generally is faster. It does not mean that it's faster in the best case scenario for linear search. It just means that it's generally faster for the general example. Okay. Another concept that is important to algorithm, what we call algorithm complexity, is the idea of growth rate. Okay. Now, what this means is that as input grows, right, then how much extra tasks are required of our algorithm. So if we think about it as, I'm sure you guys have had physics before, so you guys understand like gravitational pull and forces and stuff. So if you double the distance between two objects, does the gravitational force between them double? And the answer is no. It actually multiplies. The gravitational force does it half. Does it half? The answer is no. It actually, because of the way physics and forces work, it actually becomes a quarter of what it was before, if I'm not mistaken. It's been a long time since I've had physics, so somebody correct me if I'm wrong. Okay. And so just because the number of input items doubles does not mean that the amount of time it takes to do something also doubles. Okay. It can be a lot slower than that. Okay. So if we think of it as sometimes searching a list of 100 items, it might take 2 seconds. And so then searching a list of 200 items using the same algorithm might take 10 seconds instead of just another 2 seconds on top. And it's about the way that the algorithm works. Okay. Or it could take a lot less time than double, depending on how the algorithm is done. Okay. So the idea of growth rate is if we increase the size of the input, if we increase the number of items in our array or our data structure, right? How much more time does it take to process using the same algorithm? Okay. All right. Okay. Now, we're going to consider, let me go back to on the growth rate because an example kind of also came to mind. Maybe this might help you also. So the idea is if we're wanting to say how much more time does it take to travel from one place to another, okay? So if we're flying, let's say we would fly from Antalya, or we would travel from Antalya to Konya, for example, okay? And we would say, okay, that takes a certain amount of time. Now, the distance from Antalya to Konya and the distance from Antalya to Ankara, it depends on if we're flying or if we're driving, right? Because we can fly straight over all the roads, right? But driving, we have to take a different route. So the distance, and I guess what I'm trying to get at is the distance in terms of just a straight on the globe, put one pin here, one pin there, the distance from one place to another, flying wise is pretty linear. The distance equals, you multiply the distance by a certain amount, by a speed, and you get the amount of time that it's going to take, right? Whereas for the same start and end location, if we're driving, it's not just straight. It just depends. It depends on how many turns we have to make. If that's clear, yeah, that may have confused you more. So if that's clear, if you understand what I mean when I say that, use that as an example to help you understand growth rate. That it's not always just double the input, double the amount of time. It's not always that way. Okay. All right. So the idea of what we're going to talk about in one term that you need to become familiar with, especially we'll use this a lot in your algorithms class, right, is this whole idea of big O notation. Okay, and the idea is instead of saying, well, for an input size of 100, it takes this many tasks, instead of coming up with an exact number of tasks, we just say big O, which means it's the overarching thing that controls how much, in general, how much it's going to, how the order of magnitude. Okay, so so if it's big O of n, it means in general this is linear. It means that as we double the input, it doubles the amount of time. If we triple the input, it triples the amount of time, and so forth. Okay, and that is that an exact measurement? Like, in other words, if for a certain size input it takes 2 seconds, does it automatically mean it'll take exactly 4 seconds for double the size of input? No, it doesn't mean that it's an exact value. It just means that that is the thing that controls how fast the processing time for a set of input grows. Okay. All right. Another important concept in algorithm complexity has to do with the idea of the best, worst, and average cases. Okay. Now, what is best case? Well, best case is what is the shortest amount of execution time. So For an example on linear search, best case would be if the input is the very first item in the list. So it's just we look at it first. For binary search, a best case input would be the thing we're looking for is right in the middle of the list. Okay. Worst case is what's the longest amount of time that it's going to take. Okay. All right. So for linear search, the item we're searching for would be the very last thing in the list. For a binary search, it would be not at the, it could be at the first spot or the last spot in the list. Okay. One nice thing about the worst case analysis is that we can always say our algorithm will never be slower than this. Okay. An average case tries to determine what's the, basically what's the average, because, when we talk about, let's say, linear search, for example, we're not always going to be looking for the first item in the list. We're not going to often be looking for the last item in the list. We're usually going to be looking for something to, all throughout the list. All right. Problem with average case analysis is it's very difficult to find. Right? Because what's the probability that the thing's going to be in the first part of the list or the last part of the list or, something like that, right? Worst case analysis is usually easier to get to, and so we usually use it for the most part. Now, we would not want to use the best case analysis as something we would show, although we can show it to our customer. We don't want to use that as saying this is how fast our algorithm runs, because imagine if a company asked you to create a searching algorithm that searches an array for a value, right? And you say, well, in the best case, the thing will be in the very first item. So you know what? We can find this with only searching one time, right? That would be the best case analysis. Now, what happens if you tell your customer that, you tell your user that, and then they find out that your algorithm actually runs a lot slower than that, because they're not always looking for the first item in the list. They're going to be pretty upset, right? So instead, what we would do is we would say, okay, what's the worst case analysis? Well, in a linear search, what is the worst case analysis? What is the worst case situation for a linear search? It's the last value in the array, right? It's the last value in the list, right? So that means how many times do we have to search something in the list in order to get to the last one that we searched, the last one that we looked at? And if you're saying n, so if the size of the array is n, and we have to search the whole array, then we have to do n searches, right? So linear search, we would say its worst case analysis, its worst case is big O of n, okay? Which means we would have to do n searches in order to get there, okay? So how do we get to this? So the big O notation, what we're going to represent it as is big O of some function of n. Okay, but we want to simplify this. We don't want to have stuff like big O of 2n and big O of 2n squared plus 3n plus 5. We don't want to have like long forms. We would like to be able to have something as simple as possible inside of these parentheses. All right, so there's a couple of things that we do when we do big O notation. One is we ignore what's called multiplicative constants. So what that means is anything times something else, we can just drop that thing that it's times if it's a constant. Okay, so for example, we consider that the growth rate for n over 2 or 100 times n would be the same as n itself. Now, does that mean that something that runs in n over 2 time is going to run in the same amount of time as something of n, or in the same amount of time as something that's 100 n? No, of course not. That's not correct. But what we're saying is that the thing that dominates one set of input to another set of input is the size of n itself. It's a linear, what's called, big O of n is what's called a linear growth rate, which means that as n increases, the amount of time increases by approximately the same amount. Okay. So this is all linear. So if we look at a function of n on a graph, you'll notice that if n is 100, n is 100, n over 2 would be 50, 100n would be 10,000. All of these are linear, right? This doubles, double the input, double the time, double the input, double the time, double the input, double the time. Okay. And so basically this looks like a line on the graph, a linear. Okay. All right. So that's one thing. So if we have a multiplicative constant, we can take it out and we can be left with what we had before, with the thing besides the multiplicative constant, the thing it's multiplied by. Okay. Now we're also going to ignore what's called non-dominating terms. Okay. All right. So if something takes n minus 1 times, okay, if n is 2, it takes 1 comparison. If n is 3, it takes 2 comparisons. In general, it takes n minus 1 comparisons to find a maximum number in a list. Okay, this would be if we basically set max equal to the first item in the list and then searched all the rest of the items, the n minus 1 other items, to determine which one is the max. Okay, then in general, it takes n minus 1 times of comparisons to find the maximum number. Right. So n is the dominating term, right? If we think of it as, if you think about it in terms of calculus terms, the limit as n approaches infinity, what becomes the thing that dominates how big that value becomes? Okay, is it minus 1? Is it this thing, or is it this part? Right? If n is 2, then n minus 1 is 1. If n is 3, then n minus 1 is 2. Okay, and they're close. But as it grows and grows, okay, if n is 100, this becomes 99. If n is 1,000, this becomes 999. Right? So the thing that dominates the growth, the thing that makes the most impact to the growth, is this part right here. Right? So if we have things that sum up, and we have a subtraction or an addition to another thing, we drop it off. Okay, so then what ends up happening, if we have something that grows at the order of n minus 1, we can also say that that is big O of n as well. Okay. So I hope that's clear so far. So the big things, we take, if there's a constant multiplied, we take it off. We ignore non-dominating terms. So for an example, if I had something like, instead of n minus 1, let's say I had something that was n squared, put down here, n plus n. Okay, what would the dominating term be? If you said n squared, yeah, you're correct. That as n grows, you might say, well, wait a second. If n is 1, this is 1, this is 1. All right. If n is 2, this is 4, this is 2. They seem kind of close to each other. Yeah, but as n grows and gets really large, so let's say n is 100, which one is much bigger? This one or this one? Right? So n squared is the dominating term, so we would remove this part here because it's not dominating anymore, right? And so n squared, so if something was n squared plus n, the big O representation would be big O of n squared. Okay. All right. Some useful, helpful summations that you might just want to commit to memory. Okay. is a summation of a series, the 1 plus 2 plus 3 all the way up to n. This could be represented like this. It could also be represented as n squared plus n over 2. Okay. If we have a constant to a power up to an n, right? A to the 0 plus a to the 1 plus a to the 2 and so forth, right? It can be represented as this. Ask your calculus teacher if you want proof, if you want the formal proofs of how these can be done. We can do this using proof by induction, I believe. All right. He might like it if you ask him questions like that. Right. But a very useful one would be the 2 to the power, because in computing, a lot of times we use binary stuff. And so what is this? This is 2, right? 2 to the n plus 1 minus 1 over 2 minus 1, which hopefully you know that 2 minus 1 is just 1. So this just becomes 2 to the n plus 1 minus 1. Okay. Right. These are useful for when we start getting some of these summations involved in our big O understanding. Okay. All right. So some examples of how we determine big O from some example code. Because it's one thing if we can say, oh, you know, oh, it's n plus 1 and therefore it's big O of n, or it's n squared plus n, so therefore it's big O of n squared. But what are some real examples of how we can do this? Okay, so let's look at some simple repetition, for example. Okay, is how many times is this loop executed? Well, we would say that this is some constant amount of time. So what we can say is that it's some constant c. Okay, so this line, every time we have to execute it, right, then it's some constant amount of time for that execution. But the question that we're asking is, how many times is this executed? I'm going to make a note to myself that I want to do some of these examples like this using that whiteboard feature, because I think this would be a good example for you to understand how this would be done, how we would add this stuff up. Because the truth is that even this stuff up here is not 0 time. Setting something, you know, assigning a variable value is not done with no time at all. There is calculation power that happens there. And same thing with check, same thing with that, same thing with this. But for the most part, let's just talk about this being a constant line, and it's executed how many times? Hopefully you know this is executed n times. Okay. I'll also hope that you would know that if we did this and this, it would be the same thing. It would also be executed n times. Okay. So here this is executed n times. So it's some constant c, whatever the amount of time this takes, times n, because we executed n times, right? Which means it's cn, which we ignore multiplicative constants. This is a constant. So we take c off, we ignore that, and we say this algorithm is big O of n. A loop from 1 to n is big O of n. Okay. What about a nested loop? Well, how many times is this line? This is a constant times some constant. The inner loop is executed how many times? N times. Okay, it's right here on the screen, right? How many times do we execute the inner loop? N times. So how many times is this line executed? N times n times, or n squared, right? So we execute this. We execute the inner loop n times. The inner loop is also itself executed n times. It's not n plus n, right? Because hopefully you would understand that if this n were 5, for example, I would do this whole loop 5 times, and every time I did this loop, I would execute this line 5 times. So 5 times 5, right? So it's n times some constant for this line itself, right? Constant c times n, big O of n squared. We drop the c off. We drop off the multiplicative constant. Okay. All right. Now this one gets interesting. All right, because now we've made one little change. Instead of n here, we're going to use the outer loop variable. All right. So now how many times does this get executed? Well, the first time through, it's just once, right? It just goes from 1 to 1. So this, one time. The second time through, I becomes 2, so it gets executed 2 times. Third time through, it gets executed 3 times. Fourth time through, it gets executed 4 times, until finally I becomes n, and this gets executed n times. So it's 1 plus 2 plus 3 plus 4 plus 5 plus all the way up to n. Well, that should look familiar. That's one of our mathematical summations, 1 plus 2 plus 3 and so forth up to n times. So the summation of that is n times n times n plus 1 over 2. All right. So here, n times n plus 1 over 2. We drop this, so let's multiply it out. They multiply it out. C over 2 times n squared plus c over 2 times n. We can drop off the multiplicative constants, so we end up with n squared plus n. We can ignore the non-dominating term of n, so this becomes also big O of n squared. Okay. Again, we are not coming up with an exact amount of time that this algorithm runs. That's where a lot of us, when we're first learning these algorithm analysis things, get confused. Is we think that what we're saying is this is the amount of time that this algorithm takes to run. That's not what we're saying, because if you notice, this was also big O of n squared, right? Hopefully you know that this and this do not run in the same amount of time, right? This will run for an input of 5. This will run 25 times. For an input of 5, for n being 5, this will run not 25 times, but instead 15 times, right? Okay. So these are not the exact same amount of time. What it is saying is that as n grows, the amount of time it takes to run this is impacted by n squared. Okay. So an input of 1 for both of these ran in 1. For an input of 5, this becomes 25. The other one becomes 25. This one becomes 15. And n squared becomes a dominating factor in how much time and how many tasks are required in order to complete the processing. Okay. All right. What about this nested loop? This one's kind of a trick, right? Because the inner loop is executed not based on n. The inner loop is executed 20 times every time. All right. It doesn't matter if n is 1, if n is 20, if n is 30, if n is 100. This inner loop will be executed 20 times. So it's going to be executed 20 times however many n is. So this becomes just n. So even though it's nested loops, it's not an n squared term. It gets dominated by this. This becomes just a constant amount of time because the number of times that it's executed is constant. It's not variable based on n. Okay. Okay. What about sequence? Okay. Right. So this is executed and then this. Okay. This is executed some amount of times, then this is executed some amount of times in sequence. This line, then this line. Well, this is executed 10 times some constant. This is executed n times 20 times some constant. So we add them together because they're in sequence, we add them. Okay, nested loops, loop inside of loop, we multiply. Sequence, one thing after another, we add. Basically, if this takes 10 seconds and this takes 20 seconds, then we add them together. 10 plus 20 equals 30, right? Okay, but it's not a straight 10 seconds. It's a 10 times some constant, so that's this part of the term. N times 20 times some constant, 20 times constant times n. Right? We remove the non-dominating term, we drop the multiplicative constant, and we're left with just n. Okay, we're trying to simplify this function as much as possible. All right. One final thing we need to talk about in all this, selection. Okay. All right, so what if there's an if statement? Because it's neither a loop nor is it a sequence. It's just sometimes we do this and sometimes we do this, right? So the test time plus, so the time that it takes to evaluate this plus whatever the worst case of the if else. So we take the worst of this. So basically, remember, we're trying to go for worst case analysis. Okay. What that means is what is the, we want to show our customer, we want to show our user, this is the worst our algorithm will run. Okay, which means, yeah, sometimes it's going to work a lot faster than that. Sometimes it's going to be a lot better than that. But if you put in worst case input, this is you can be guaranteed this is how long it'll take. Okay. And the reason why this is important is because what we do for a selection is we look at each side of the selection for its worst case. Which one of these is worse than the other? Okay. Well, is this, how much time does this take? And if you say this is just a constant amount of time, you're right. Right? Because why? If it's E, if it's some element, to print our element should just be what, 1, right? It's just a single constant amount of time. Okay. So that's one choice, is constant time. The other choice is a loop where we go through all the items in the list and we print them all out. Okay. How much time does it take? If our list size is n, how much time does it take to go through the list? And the answer is n. So this is constant, this is n. Which of those is worse? I'm really, really hoping you guys are all with your microphones off saying the second one is worse. Right? And because you're right. The second one is n is much greater as a dominating term than this. So the worst case, that's this part over here, the worst case of the if else is big O of n. So now we need to add that to what is the test time. Okay. In this situation, the test time, if the list contains our element, right, big O of n. Why? Because we're searching the list to determine if E is there. Let's assume that our search is a linear search. Okay, it's not a sorted array, right? So we can't use binary search, but our list is unsorted. We have to search through the whole thing possibly. Our worst case of our searching through the array, through the list, is n times. All right. So the test time is how long does it take? How long does it take to complete this? Our worst case of the if else is which one of these two is greater. So big O of n plus big O of n. Notice it's not 2 big O of n. It's just big O of n itself. It's whichever one of these, basically, which of these terms is dominating. Right? And hopefully you recognize that big O of n is the same as big O of n. So neither of these is dominating. It just basically runs. Right? It just becomes big O of n itself. Okay. All right. Again, I'm going to go ahead and I'm going to end our time on the lecture there. Okay. We'll talk about constant time tomorrow, whenever we come back to this. All right. I am also going to create a, like I said, a whiteboard style example for for some of these to be able to show you in better detail of how this works, of how we can take an exact amount and showing that those loops, big O of n, and those nested loops, big O of n squared. Okay. Other than that, if there are no questions, then I will go ahead and end our lecture time for today. And by the way, I'm surprised it hasn't been posted yet. It should have posted now. I don't know why it hasn't. All right, but you guys have a quiz that you have until 1:30 today to complete. Okay. And so I would like you to go ahead and do that. It's a Google form. You should have just gotten a notification about it being posted. All right. And so go ahead and do that. You'll have until 1:30 to complete that. Because I warned you about this quiz last week, I will not be able to accept any late submissions. All right, so make sure you get that done by 1:30. None of you should have any classes from the 12:30 to 1:30 slot. That was a free time for lunch. You can do this quiz while you eat. Okay. All right, so again, if there's any questions related to this lecture or related to the stuff I talked about at the beginning about the midterm assignment, please let me know. Get those in sooner rather than later, because that midterm assignment is due, I believe, Sunday, right? So, all right, make sure you get to those sooner rather than later. All right. Thank you guys for attending, and I will see you tomorrow morning.